Well, first of all, good morning and thanks for showing up. It's always hard being the first talk after the banquet in the morning. So thanks for really getting up to listen to my story. Thanks to the organizers for inviting me and also for putting sustainability on the agenda on this conference. It's something that is very close to my heart, and I really appreciate having the opportunity to give you my view on where we are and what biotechnology can actually do for the green transition that is so needed. The Novo Nordisk Foundation, the vision is to improve people's health and the sustainability of the planet, or planetary health, as you could say. And despite the fact that we are one of the largest foundations in the world, handing out more than €1 billion last year, the foundation is not that known in many parts of the world. So I take the liberty to actually take you down history lane, which actually goes 100 years back in time, when the gentleman you see here on the picture, August Krogh, he received the Nobel Prize in 1920 for his discoveries on how the capillaries in the body regulate the oxygen transfer from the lungs to the tissue. On the picture you also see his wife. She's an interesting lady. She was the only fourth woman in Denmark to receive a Ph.D. She was actually contributing a lot to the work that he did. And in 1922 they were touring the US on a lecture tour to tell about their research. And during that tour they learned that people in Toronto, scientists there, had managed to extract insulin from animal glands and treat diabetes patients. And Marie Krogh, she was actually a diabetic. And at that point of time, there really had been no treatment for diabetes, except living on a very strict diet and looking forward to a way too early death. So they managed to take a little detour to Toronto, and they also got a license to produce insulin for the Nordic market, and the license was free, under the conditions that the profit of their operation would go back and benefit science and society. So they went back, they managed to get production up and running in 3 months. Those were the days, right? Get it to a pharmaceutical product in only 3 months, and could actually treat diabetes patients. Then there was a long story when people very rapidly left the first operation, Nordisk Insulin, formed a competing company, Novo Industries. These two operations were then located 7 kilometers apart in Copenhagen and were fiercely competing and had a love-hate relationship a love-hate relationship without a lot of love, to put it bluntly, for almost 66 years, I believe, until these two companies merged in 1989. And that was also the point when the two foundations that were kind of actually taking the profits from those two operations, handing it back to society, where they also merged and formed the Novo Nordisk Foundation as we know it today. The foundation has a philanthropic part, that's where I work. Then we also have the other part that takes care of the investment, and they have the voting majority of the Novo Group companies, Novo Nordisk, and now the Novonesis, the company that used to be Novozymes. And they have then invested in another 170, 180 companies by now, and really is a good investor in that space. Interestingly, also Novozymes was actually kind of started as a byproduct from the insulin extraction from animal glands. The enzymes coming from the pancreas could actually start this industrial biotechnology adventure. And the foundation is working across the whole value chain, all the way from education of primary pupils through a lot of research grants, over innovation grants. There is an incubator facility. This is too complicated for me, the pointer. Going then into going into the holding part that is then investing at all different kind of levels in industries. And in many cases, to drive change in society is not a question about just handing out money in research grants. What is often more important is actually to have investors and good investors that can do a thorough due diligence and actually be a good owner with a long-term perspective. And we have three focus areas in the foundation. Cannot be a surprise that health, of course, is important for a company that is based on diabetes, or a foundation that is based on the revenue from diabetes treatment. So cardiometabolic diseases is definitely a focus area, but also recently infectious diseases has become more prominent. And the COVID pandemic we had a few years ago really promoted the foundation to also now work in infectious diseases and preparedness for handling in the pandemic situations. Then there is the life science ecosystem that is to a large extent a very Danish thing, where we support academic institutions to actually educate people and to secure that there will be a good workforce for the bio industry. And the third aspect here is also where I work, is then the sustainability part. And clearly what we see with global climate changes on the globe is that is also becoming more and more connected to health and people's well-being. If you have cardiometabolic diseases, increasing temperatures is not really good, and you see actually that the heat wave we experience now and then actually has devastating effects on people, and people are actually dying due to the climate changes, not to mention all the other weather phenomena that we observe in this world. In the sustainability part, or kind of to rationalize why the sustainability part is so important, we all know that we have a growing population. By 2050 we will be around 10 billion people, and we expect that the population is likely to peak around 12 billion people. All these people, of course, have to be fed, they have to live, they have to have houses, that of course put even more pressure on the planet we are living on. And what we will also see is that our greenhouse gas emissions are steadily increasing, such that we expect that the CO2 emissions by 2050 is going to hit 50 billion tons of CO2. And actually that number is pretty much where we are currently with if we consider also all the other greenhouse gases, some of which are actually worse than CO2, but CO2 is the one that has the highest concentration. And our whole food system is pretty flawed actually. A third of our greenhouse gases comes from our agriculture food supply chain. And we also see that most of what we actually grow out in the field is spent on feeding livestock in order to make meat, make milk, very, very nutritious food, but it has really a lot of impact on the climate and the way we live. And furthermore, our agricultural practices, where we have huge areas of monocultures, also have a devastating effect on our biodiversity, which is a crisis that is of similar size or as severe as the climate crisis that we are facing, and these things are connected. So that's why we have decided to focus on 4 areas in the sustainability part of the foundation. 2 of them is, as I said, related to the agriculture, the food supply chain. There's a lot of improvements that can be done there. We have the third theme is more on the industrial production. How can we convert producing everything today that comes from fossil material? How can that be done by biological processes? It's also related to how do we capture CO2 in the atmosphere and utilize that for something useful. And all these 3 themes are, say, technical. That's where I feel confident. I'm a scientist. There are a lot of great technical solutions out there. But how to get these implemented in society is a completely different story, because this is definitely not trivial. We can produce pretty much any kind of goods we produce today by biological methods, but making economy fit is really a challenge. And there's also the aspect that we are, as a society, subsidizing the wrong living. approximately 7% of our global GDP is spent on subsidizing fossil materials. Try to imagine that we would actually spend this money subsidizing green production. In the same way, a European cow receives €2 a day in subsidies. That's a lot of money. It's more than an average African farmer makes a day. And if I want to eat meat, and I have to admit I do, my neighbors should not pay for my beef consumption, right? I mean, a steak should cost what it actually costs to use it. And just to illustrate, how the greenhouse gas emissions has developed, it's, as you can see, last year was the year we emitted the most greenhouse gases on the globe, despite all the efforts we have done in actually to change and go away from fossil material. Still, last year we produced or generated more than 50 billion tons of CO2 equivalent. This could be a fairly devastating picture to show, but I'm actually an optimist. And if you look down here at the bottom, what the situation has been in Europe, you actually see that CO2 emissions or greenhouse gas emissions is declining. And in Denmark, the country where I come from, since the emission peak, now we are approximately at half the level where emissions were when it peaked. So there are things that can be done, and we can change this picture if we want to. But these are just numbers. So try to work with me on a little mind game here. If we converted all the fossil material that is being generated to coal equivalent and made a cube out of that, that would make a cube with a side length of 3 kilometers. That's a fairly big thing, right? And so maybe it would not be as severe if you spread it out over, say, the land mass of Denmark. That would create a layer of 0.5 meter across Denmark. Denmark is it's a very small country, right? If you took Poland, that is 8 times bigger, then it would be more like 6-7 centimeters, right? Every year. And I think that would really be a nasty thing to do to your beautiful country. So just to illustrate really how much fossil material we use on a yearly basis. The way my world, and this is definitely a simplified picture of the world, and the way we use carbon is cyclic. For 150 years, we have generated prosperity based on oxidizing carbon we get from the underground. And that has, of course, created a lot of CO2 in the atmosphere. We have approximately 1,000 gigatons too much carbon in the atmosphere now. And that carbon is actually, by photosynthesis, beautiful process, converted to biomass, that eventually will become geological reservoirs and become oil, gas, coal. The problem is kinetics. This process takes in the order of 1 million years. So that's why actually we see this accumulation of CO2 in the atmosphere. Biomanufacturing has the possibility and does shortcut this carbon cycle. So sugar coming from agricultural products and protein containing nitrogen is used in biomanufacturing to produce all the things that we use today, from bioethanol to our food. Many of the chemicals we use today can actually be produced by biomanufacturing. But the problem here is that if we have to replace all the fossil material with sugar coming from agriculture, we run out of land. And we should actually reduce our land use to also help the biodiversity situation. So that is not really a solution. Well, it's part of the solution, but the ultimate picture that we have is to try to reutilize the carbon dioxide that we have excess of and use directly in the bioproduction. This looks really, really simple on a schedule or on a graph like this. Very nice, short, circular system here for our carbon use. It's of course not that trivial, because in order to reduce all the CO2, which is a very energy depleted molecule, it takes immense amount of energy, electricity, electrons that has to be used to carry this out. That is electricity we don't have today, but also illustrating why it's so important that we have a lot of focus on enhancing our production of renewable energy, whether it's wind, whether it's solar panel, whether it comes from nuclear, debatable, but I think we need all of these to supply enough electricity to actually, drive this conversion to a more circular or a better circular carbon economy. In order to make this fly, we also had to work on making our biomanufacturing a lot more efficient. Today, biomanufacturing works really well when you produce high-value stuff like industrial enzymes or pharmaceutical products that has a high kilogram price. But if you want to have a big impact on the climate, you also have to look at large volume chemicals, stuff, material, food, etc. That calls for way more efficient and cheaper biomanufacturing in order to drive this process. And there's a lot of critical questions on how do we do this? How do we demonstrate the viability and also the sustainability of alternative ways of making biosolutions and producing biomanufacturing? There are technical issues. There's a question about energy, as I alluded to, as well as the economy of the whole process. And because something is done by biology does not mean it's necessarily is more sustainable. So it's also important that we constantly are aware of the economics and the sustainability of the processes we are trying to implement in society. And there are some crucial questions here. How do we generate the electricity? It's a very important one. But equally important is how to get the electricity or the electrons into the biological processes such that maybe you don't have to go via hydrogen, that is a typical solution today with power to X. What are the relevant renewable substrates? Of course, CO2 is the dream scenario of the carbon source, but other waste material can be upgraded through a bioprocess to something more valuable. And then, of course, we have to find out what is really waste. Is corn stovers on the field, is that a waste? It can also be used to put in a biogas plant and then generate energy for society. So also finding out what is really waste. Then the problem we face every day is which biosolution is it that we should prioritize. Often, and what is really great is when we have smart biotechnology solutions, when we replace a chemistry that is used today with something that is smarter and demands less volume of material. It could be if you can replace, say, fertilizers in the agricultural practices by microbial systems that can help the plants assimilate nitrogen. It could be to replace pesticides and plant protection agents, again with microbes that maybe can outcompete, the pests, and that kind of, smart biotechnology solution. Eventually, we will also get to the situation where we have to replace large volume chemicals with, one-to-one replacements, because there are a lot of chemicals that we actually do need and food sources that we do need. And how do we do that? And then scaling is actually the really big questions here. How do we scale these processes? Because as we all know, biomanufacturing is really expensive, both from a CapEx and from an OpEx perspective, calls for making the biomanufacturing a lot more efficient. And then finally, getting these new technical solutions implemented in society, where that takes collaboration between industry, academia, government, NGOs, basically everybody, in order to change the way we live and to change our priorities, also how we live our individual life and what we prioritize here. So this is the, fairly simple way of looking at the world, in which input, which is substrates and a lot of energy, via biomanufacturing, create something that is more valuable and preferably really high volume products. And what are high value or high volume products? Well, if you look at our food, what we eat on a daily basis, milk is produced at approximately a gigaton a year. Of course, there's a lot of water in milk, but also if you just take the weight fraction of milk, it's 160 megatons. That is something that could be very attractive to replace with a biotechnology solutions. Our whole way of making, buildings, roads, constructions, huge volumes, that is very attractive but also very difficult to address. And then some of our consumer goods, 450 megatons of plastic is generated every year. Again, that's just a number. It's more or less the same as the weight of all humans living on the planet, which means that we are kind of, all of us, responsible for our own weight in plastic every single year. And since we live in the more prosperous part of the world, I think most of us can actually account for more than our own weight in plastic. Something we ideally should do something about. Ammonia used for fertilizers, 250 megatons a year. So just some examples of some really high volume but hard to get materials, chemicals, food. And there are a lot of technology components in driving cheaper biomanufacturing. All of these, like culture optimization, they are not all equally important. For instance, the microbial cell factories has actually been pretty much perfected over the last 20 years. Goes really well these days, whereas a fermenter looks like a fermenter looked 50 years ago, and it's more or less the same technology. Downstream processing can easily be more than half of your production economy. Again, an area that calls for a lot of new developments, and all of these things, of course, have to be thought into holistic solutions in order really to drive cost of biomanufacturing. So the way we look at the world is to have technology competency centers, hopefully in a European setting, and to make these competency centers collaborate on driving the right solutions. That likely means that these competences have to, first of all, not try to build up every competences themselves, but they have to have sufficient overlap also to be able to really collaborate efficiently on solving real-life problems. And I would like just to highlight 3 examples of things we are supporting. 2 of them are research centers. The CO2 Research Center that was established 3 years ago at the University of Aarhus in Denmark. And then the newest kid on the block, BRIGHT, Biotechnology Research Institute for the Green Transition. Very long work, say BRIGHT from here. A grant that was given December last year. So this center is being established at the University of Denmark. And then I would actually like to start with one of those collaborative projects that we call the Acetate Consortium. And that addresses the supply of nutritious protein for human beings across the globe. As I showed earlier on, our food supply chain puts a lot of stress on our climate, on our planet. So how do we find an alternative way of producing nutritious protein for an increasing global population without making more agricultural products and spending more land on that, while at the same time reducing our greenhouse gas emissions? The way we typically look at food production today is that photosynthesis uses CO2, generates sugar. Sugar we basically feed to animals, and then we eat the animals. The vision here is to convert CO2 in an industrial scale to acetate, and there are many ways this can be done, and then use the acetate rather than sugar as a fermentation substrate to produce protein in a tank. And this is a bit of an unusual project for the Novo Nordisk Foundation. Typically, we support TRL 1 to 3 level research in academia. Since here we are working more on driving technologies from TRL 3 to TRL 6, We have decided also to include industries in this work because industry is typically very good at scaling. So you see a couple of Danish companies, Topsoe and Novonesis, engaged in this work, an American company, Novonesis. We collaborate with the Gates Foundation on supporting this, where the two foundations each put in approximately 15 million euros to drive this for the first 2 years. And there are also then academic teams engaged in this, including the CO2 Research Center at Aarhus University. And what is shown here on this panel here is the various ways to generate acetate. Topsoe is working on a electrochemistry-based process in which hydrogen and carbon monoxide is derived by electrolysis. The hydrogen is used together with CO2 to generate methanol, and methanol and carbon monoxide can then, in a chemical process, generate acetate. The Novozymes company and University of Washington is working on a two-step electrolysis process. First, converting CO2 to carbon monoxide, and then carbon monoxide in a second electrolysis step to acetate. And the CO2 Research Center is working on a purely biological process, a two-step fermentation process in which an acetogen is converting CO2 and hydrogen into acetate, and then the acetate is used in an aerobic fermentation to produce edible protein. And the last part of converting acetate to protein, acetate is not a really traditional fermentation substrate, so most organisms don't really like it. So Novonesis, that has some of the best expression systems in the world, are then trying to change the metabolism of these cells to work as efficient on acetate as they do today on glucose. We don't know which of these technologies that will be the winning one, but we are betting, say, on parallel tracks here to find the most cost-efficient way of producing acetate. This shows the two-step fermentation process. First, the anaerobe one, carried out at high temperature. This would be a continuous process. In order to also optimize economics, it's very important that everything is being utilized here. So the CO2 that is a typical product in an aerobic fermentation will be cycled back and be a CO2 source together with CO2 coming from some kind of point source in a substrate in the first stage. And the oxygen that is a byproduct of the electrolysis when you generate hydrogen can actually be used to accelerate your aerobic fermentation and make that a lot more efficient. So the CO2 Research Center is now in the process of installing a 2 times 100 liter fermentation pilot, such that it can actually generate as good data to support the further implementation of this process into a demo plant. And it's really, really important that energy and streams of material is optimized in this process. And since I am a little bit pressure on time, this is just kind of the roadmap towards, hopefully eventually we will end up producing this in megaton scale across the globe, serving both the nutritional needs of people in the Western world as well as in emerging economies. An important aspect I have not mentioned yet is that protein also has to be delicious. It has to be preferred by humans in order actually to catch on. So we are now also in the process of engaging food companies in trying to find ways to make really delicious food in various geographies that will be preferred by global consumers. Do we have enough CO2? Here are some examples of, yes, you could get it from the atmosphere. That is very, very dilute. It's very costly, both financially and energetically, to get CO2 from air, the so-called direct air capture. So initially, of course, the idea is to use a point source where the CO2 is more concentrated. That could be biogas plants, anywhere from biogas plants to cement plants. And ideally, we think that bioethanol plants are an ideal place to start. because the CO2 is actually fairly pure from an anaerobe ethanol fermentation. And if you look at a typical bioethanol plant here that emits a little bit short of 300 tons of 300 kilotons per year of CO2, that could, with the efficiency of this process, generate approximately 46,000 tons protein per year, which is enough to actually supply approximately 2 million people with their daily need for nutritious protein. Now, changing gear to the CO2 Research Center that was established 3 years ago. This technology center is kind of technology agnostic. So it works both with biotechnology as well as chemical enzymatic systems in order to capture CO2 and concentrate it, and then use the captured CO2 for something useful, the utilization part, which could be food protein, as I just described, but it could also be production of any kind of large volume chemicals we are using today, turning into bioplastic, whatever. And I borrowed 2 slides from some of the scientists working at Aarhus University and University of Copenhagen that are working on some really smart ways of maybe using some of the waste plastic we have in society. So they're trying to work on nitrile butadiene that is used in a number of the products we meet on a daily basis. And what is shown here on the lower to your left panel is how real-life plastic material has been chemically converted into CO2 capturing material. And you go to the right bar here is a little bit kind of a reference point of what is used commercially today. And you can see that, we are not really far off with the efficiency of these materials. And what is shown in the middle panel, lower middle panel, is how these materials can actually be recycled. And of course, these have to be recycled in many ways. So here it's kind of 2 birds with 1 stone. We can get rid of, or actually take plastic waste from Lego bricks, rubber gloves, toothbrush handles, various places, and use that to generate CO2 capturing agents that we really need in this world. Another example is the Center for Biosustainability, also a really large operation that has been supported by the Novo Nordisk Foundation for 15 years now. They have worked on perfecting how to use genomic information to manipulate the genomes of microorganisms to be able to produce basically any kind of material we use today. And they've been very successful, and that's also why I say that likely the cell factory is not where we need to actually invest most of our attention, most of our money and most of our attention currently. And now we are in the process with the grant to write. There was a grant that was given December last year, 134 million euro over a 7-year period to try to have a university establish an operation that works on solving missions. And that is not a traditional thing for a university to think on applying the academic competences to solve real-life problems. So together with the Technical University of Denmark, we are trying to implement a center that will utilize all the competences that are found in an institution like the Technical University, and have these come together and collaborate on working on finding solutions in 3 areas: sustainable materials, including energy carriers like batteries, microbial foods, and how can you engineer microbes for agricultural purposes. 3 very important areas where there is a lot of potential for actually impacting sustainability of society. And then finally, which is completely shifting gear and not something that the Novo Nordisk Foundation should take the credit for, is industrial symbiosis. Kalundborg is a city in Denmark. If you know Zealand, where Copenhagen is way to the east, if you go straight to the west, when you hit the coast, you would meet the city of Kalundborg. It's one of the major industrial hubs in Denmark, where both Novo Nordisk and Novonesis have their largest production facilities, plus a number of other industries, from oil refinery to now a biogas plant, a company that produces gypsum. And they started 50 years ago to actually look at a situation where waste from one industry can be used as a starting material for another industry. Energy, wastewater at a certain temperature can actually be come into use in a different industry. So now it's more than 20 streams of water, energy and materials that is being circulated between these industries. And I really like the fact that 50 years ago, before the term industrial symbiosis was even invented, these companies started to working in a trustful relationship on utilizing each other's waste streams as input to their own production. Also, finally the cooling water coming from this whole operation then actually serves as heating, for the city of Kalundborg. And right now, they're actually considering making a pipeline all the way to Copenhagen, because there's still excess energy, from the production in Kalundborg, and that will be a fairly long, that's approximately 100 kilometers, so a fairly long pipeline to actually utilize the waste energy. So with that, I would like to conclude my talk saying that although it may be a bit of a gloomy picture I'm painting with respect to where we are on climate, on biodiversity, I'm still an optimist. I believe that biotechnology, biosolution, biomanufacturing has a huge role to play if we do it right. It's not a walk in the park, it's not easy. We will have to work together with society, make sure that we actually secure that we subsidize the right way of living, and then find solutions between all of us in collaboration. So with that, thank you for your kind attention, and if time allows, I will be happy to answer any questions.
Thank you very much, Torben. Nothing ever worth doing is ever easy, I suppose. So, any questions for our keynote speaker guest today? Now's the time. I know it's still a warm-up phase for day 2 after a long night, but let's give it a try. One question, at least, hopefully. We'll still have extra time, after which we'll have a short break.
Hi, amazing presentation, I'm impressed. And I have one question about this last part of your presentation, about the symbiosis. I'm wondering who initiated this action. I mean, there was a lot of companies and you integrate them in one ecosystem which is operating with the waste streams, different waste streams. So how it begins? I mean, if you could give us a short answer.
Oh,
Torben, I can give you my microphone, maybe?
thank you. That's a really good question, because at that point of time it started, of course, with fewer streams of material, and then it has kind of slowly been expanded, to cover more and more streams. Later on, a biogas plant has been implemented to take care of the fermentation waste coming from Novo Nordisk, Novozymes. Early on in the process, these companies would actually inactivate their fermentation material that is not used in products in order to kill the production organisms, and then that was handed away for free to the local farmers as fertilizers out on their fields. Now it's believed that it would create more value if it's being converted to biomethane. That can then, of course, again be used to create steam for the production, then again in a cyclic fashion. So it started off with a few companies, including the municipality of Kalundborg, and the municipality has been extremely helpful in this process in supporting setting up this whole system, because it's also the municipality that is responsible for the environmental approvals that of course is needed to do this. So the municipality has been very helpful, but it started off with some visionary industries, and they're actually, the Novo Group has been fairly visionary in this when they started up the really large-scale production in Kalundborg, and could see that fermentation per se is not necessarily that sustainable, because you lose a lot of water, you generate a lot of biomass that has to be used somehow, and that was kind of what triggered this whole cyclic setup. And then it has just been added on, one industry, one stream after the other, and really taking off. So it has been maybe not as seen now, it looks like a revolution. It has actually more been like an evolution, slowly developing over 50 years.
Do we have any more questions?
May I?
Swap the microphone. Anyone else would like to ask a question? Magda?
Yes. You're saying about the evolution right now in this field, at least, but we are also witnessing the revolution biotechnology regarding all the new techniques that you also mentioned, synthetic biology, data-driven revolution. How Novo Nordisk Foundation is implementing those new revolutionary findings, and you highlighted some examples. If you could elaborate more, maybe. And that's my first question. And the follow-up question would be, how is it possible to cooperate with Novo Nordisk Foundation regarding implementing those new techniques in your pipeline?
Yeah, that was a lot of questions in one go. I'll try to see if I can remember all of them. In the foundation, we don't invent anything. I mean, we are just 250 people sitting in a nice glass building in the outskirts of Copenhagen. So a lot of what we do is actually being out there and getting inspiration from all our partners, and predominantly academics, startups, established companies, on getting the ideas on what can have a large impact. The faster, the better. It may be risky, or actually I would say it should be risky. If it's an established technology, it's not for us to support it, then it's for industry to grab it and scale it. We are looking for the small revolutions that has huge impact for changing the overall economics of biomanufacturing. So one example is gas fermentation. We would like to go away from using sucrose and agricultural products as a fermentation substrate. There's not a lot of really great, economically viable gas fermentation production in this world. There are some companies appearing, like Lancetech. They use predominantly the flue gases from steel mills to produce ethanol, and the ethanol is further converted to sustainable aviation fuel. It's a beautiful technology company. They have really done a lot on gas fermentation. They have worked a lot on engineering the microorganism to optimize the use of predominantly carbon monoxide, because there's a lot of carbon monoxide in steel mill flue gases, which of course is a way better substrate than CO2, it's more energy rich. So we are looking at, say, the various technology components that are needed, and there are many places. There we have open thematic calls, which currently have some geographical restrictions. Currently in the industrial space, industrial environmental space, it's confined to applicants from the Nordic region. We are currently considering whether that could be broadened out to Europe. It of course will come some complications, because it would also mean that you get a lot more applications if you broaden to a wider geographical region. Many of these calls also call for collaboration, and where collaborators could come from anywhere. And we really appreciate that in the proposal because we would like to employ the brightest mind in the world to solve these global challenges. So these are the open calls that are thematic. They are, and many of them are coming out regularly. Then we have the Champions League of our open calls. It's called the Challenge Calls. That will be called for once. We have one call every year, and then it will be one specific theme that we think is very important. Last year it was heterogeneity in biomanufacturing. That was the theme. And there people could apply, and there would be a grant of around 8 million euro over a 6-year period. Typically there would be a Danish applicant and European partners participating in that call, and that is just being finalized right now, who will be the grantees from that call. In parallel to that, we have what we call standalone grants. That are things we co-develop with applicants, and their ideas can come either from academia. They come to us with good ideas, and if it's something that fits our strategy, then we will try to work together on finding a good proposal, on really solving something that is really important for, in this case, biomanufacturing. And then again, that could be anywhere in the world with the applicants. And then, of course, in some ideas, we even get an idea now and then we try to find out who are the leading experts in the world that should work on this, because we really want to have the global minds employed in solving the large global problems. Did I answer all of your questions? Amazing. Thank you.
It really was amazing, wonderfully specific and thought-provoking. Thank you. Thank you, Torben. Unless we have one more question? No. That's it.